Welcome everyone, benvenuti e benvenute. Chiedo scusa per il ritardo. I apologize for the delay. I'm going to start speaking in English for now. Today our language is in English, since this is a seminar for basically our master degree students here in Edolo in presence, but also for people connecting from remote. Again, apologies for the delay. So we will postpone the ending of the webinar. It will still run for 2 hours. So we plan to finish by around 4 p.m. We have a speaker today, Marco Mina, Dr. Marco Mina from URAC Bozen, private research institute here in Italy, not very far from here. Marco is still setting up his presentation. So in a couple of minutes, he'll be ready to start the talk. I'm Giorgio Vacchiano. I'm a professor in forest management and planning here at Università della Montagna Edolo and University of Milan. And I'm also a teacher of this master degree in valorization and sustainable development of mountain areas. The topic for today is modeling forests. Forest modeling, forest simulation, using computers to forecast and understand how forests will develop. And I think this is highly needed in times of climate change, when we cannot rely on the past anymore to understand how forests are behaving or will behave, how many ecosystem services they will continue providing to us, but we have to understand what new dynamics and new processes forests will undergo in a different climate, in a climate that is rapidly changing. And Marco is an expert in forest modeling. He's running different projects. I'm sure he will illustrate some of these projects as case studies and show how, in fact, computers can be a very useful support for practical forest management and especially forest planning. So for professional foresters that are connected and also for students, it's not very common yet, in Italy at least, to use computer models. Please, Marco. To use computer models as a support for management, but we're getting closer and closer to a point where these models get out of the university lab and are more and more accessible to foresters. And then maybe you can discuss how accessible they are, how easy it is to use them for the average technician. I think it's an interesting point. Okay, so I think the presentation is ready. Marco, the floor is yours. We have 2 hours to stay together, so we will certainly have questions, both from the floor here and from the panel from remote. People from remote can certainly type their questions in the chat box, and then Alessia will help us reading them out. And then students can also interrupt, I think, with questions at any time. The only attention I ask from you is if you have questions, maybe we will hand you the microphone. So also people that are following us from remote will be able to hear the question and then the answer. Marco, the floor is yours.
Thank you so much, Giorgio, for the nice introduction. And then I will reintroduce myself, because I always have a slide about myself, because I don't know, I like to people know who is talking to you today. So today we're talking about modeling forest dynamics, and with a particular focus on management under climate change. That has been the topic and the focus of my research in the last years. Okay, so just shortly about me, I studied forestry and environmental science at the University of Padua, but I grew up academically more in Switzerland, where I did my PhD in forest ecology under the supervision of Professor Bugman, who is a well-known modeler. He has developed several models of forest dynamics. That's where I specialize more in the use and the application of these tools in the context of forest and climate change and adaptive management. Then I did a short period of postdoc in WSL, which is another institute in Switzerland. And then I had the chance to develop my own project in Canada. I moved to Montreal in Quebec, in the eastern part of Canada, where I sort of expanded my scale of application. Before I was using models at a stand scale, then I applied more landscape scale models. And since 2021, I'm back in Italy, and I'm a senior researcher at URAC, which is an interdisciplinary research center in South Tyrol. Because we have it's located in Bolzano, so it's a sort of it's an institution, it is private, but is also highly promoted by the autonomous province of Bolzano. We have two headquarters, the main headquarters, and then one at the Neutech Park, where there is this famous Terra X Cube. It's a very special climatic chamber where they can recreate climate at a very high altitude, and it's used by some specialized institutes like the Institute for Mountain Emergency Medicine. These are all the institutes that we have at URAC, so it's a very multidisciplinary. In our case, I work at the Institute for Alpine Environment, and even if it's one institute, so we are 600 employees in URAC. Within our institute, we are also quite heterogeneous. So our focus is alpine socio-ecological systems under global change, but there are people working on plant ecology, soil ecology, animal ecology, limnology, landscape ecology. In our case, we are building a small group in studying forest ecology, particularly with the use of models. Okay, done with the short introduction. I usually, when I talk about models, I divide my seminar, my lecture into three parts. In the first one, I will try to give you an overview on how models were built. So the history of forest dynamic modeling, how did we decided to put within a computer the so-called yield tables to develop our complex simulation models over time, over history. And then we can stop. We can have some Q&A if you want. Happy to elucidate some of your questions that you might have. And the second part is more about research applications, where I will bring you a lot of examples on how these models can be applied to study forest dynamics under climate change and management. And with a particular focus on three models that I've been using in the past years. And then there is the last part where I will show you what are we currently doing in South Tyrol, give you an overview of the region, and our current research activities and projects that we are currently developing at URAC. All right, so again, introduction of the introduction. So we know, I mean, if you study, what is the name of your course of study? Valorization of mountain area. Yeah, so you know better than me how important are forests because they provide a wide range of ecosystem service. They provide timber, they provide non-wood forest product, they support habitat for biodiversity, cultural ecosystem services, which are key in our region, for instance, in South Tyrol, where we have a lot of tourists. Forests, they also need to be looking good for people that spend a lot of free time on them, but they also, particularly in mountain area, they regulate, for instance, they protect against natural hazards and they store carbon from the atmosphere. But we cannot really detach the studying forests from their management, because particularly in Europe, which is a continent where forests have been heavily managed in the past decades, in the past centuries. So the forests that we see them now, they are really the legacy of past management interventions. So that's why when we go to some other new, more new continents, like also North America, the forests are much more complex in terms of species, because here the forests have been heavily simplified from centuries of interventions. So but it's not, on the other hand, it's not so easy to plan management interventions, because managing forests require knowing series of factors that influence our management decisions. That can be abiotic factors, what is the climate of the area where we are going to intervene in our forest, biotic factors, for instance, that a broadleaf forest is managed differently by a conifer forest or a mixed forest. But also there are many socioeconomic and political factors like restrictions. There are what is the ownership of the forest, and this drives management decisions. And if in the past we sort of knew how to manage forests, nowadays the situation is getting more and more uncertain, because the climate is changing much faster than the adaptive capacity of forests to adapt to a new climatic conditions. And we are, it's not only the effect of climate change, the direct effect of climate change that we have to fear, but also the indirect effect of climate change that I will talk later on. So the related disturbances that can occur to our forests that can cause a loss, sudden loss of all these important ecosystem services. But if we go back in time, I like always to show this timeline of forest management systems. In the past, mostly management was directed into sustaining a few tree species. So it was more, had only the objective of educating the forest to produce timber, which was the main ecosystem service. Forest equal wood back in the 1800, early 1900. Still, this needed to, even with the simplified objective, which was mostly executed at a standstill, the foresters needed to have some projections that were based on past observation to know where and how to intervene and how much to intervene in a forest to not to intervene too much, so to deplete the sustainability of such forest. And this stimulated the first models. And the first models are the so-called yield tables. And yield tables, also called growth and yield tables, they were the first attempt to put into numbers the growth of a particular forest stands. And this is simply, if at the beginning were simply the number of trees or the number of the volume of a particular forest stand, then they slowly evolved into becoming these tables that are able to predict the amount of yields, the amount of not only of yields in terms of volume, but in terms of also of revenue at the financial maturity of the forest stands. So these were the very first, if we want to say if there is a precursor forest model, these are the so-called yield tables. So even they were on papers, they are in a way the oldest model in forestry. And with their limitations, they were still the most positive advance in forest research in history. But as you can understand, these yield tables are very non-generalizable. They are region and site specific. So they're very static. So they are based on past observation, and then they can give some predictions, but in a very short term. And then they cannot be used for making extrapolations. So these yield tables are only valid within the range of the local conditions for which they were developed. So they could not be used for making predictions if climate is going to change, and also for considering the intraspecific interactions that we have between tree species or even proveniences or varieties that we have in our forests. Despite this, some yield tables are still used today, not as in a fashion form as you saw before, but for instance, when I spent my postdoc years in Quebec, I realized that for some areas of Quebec, foresters were still using Excel sheets based on the financial growth that was based on some equations developed many years ago, while I was at the same time trying to use a very complex simulation model that takes into account climate, disturbance, and all the other factors. In reality, foresters are still using them, and often they are not well documented. So we know that for instance, these softwares give to private foresters or also for public forests the allowable amount of volume that can be harvested for a particular forest stand, and then the foresters take it as granted, but sometimes they don't know from where this the calculation come from. So yes, in some cases are still used today. Although already from the 1970s and 80s, something started to change in the forest management world. So we started to recognizing more the need to not only optimize timber, but also to maintain other ecosystem services. We started to understand that we needed to tolerate adaptation of tree species and to sustain more a natural tree species composition and that can accommodate biodiversity. And this required to, first of all, to see forest management at a different different scale, a different spatial scale. So to move from the concept of managing stands within a landscape, but seeing the stands within the forest landscapes, and also to better understanding what is happening in the ecological interactions in our forests, which are, they may look very simple, but they are very complex. So for this reason, some foresters started to dynamicize, if we can use this term, these yield tables that were already, with the advent of the first personal computers, being made in a computer, so they were not on paper anymore. But then they started to develop the first empirical individual tree models. So if you want to simplify these yield tables, there were some models that became they are the natural successors of the yield tables. And here we start introducing the topic of the day. The topic of the day is forest modeling. And before knowing what do I mean by forest modeling, we should know what is a model. A model is a simplified representation of reality in mathematical form. So we can really model anything. We can model weather conditions. Also, we know that the weather forecasts are based on atmospheric models. But in our case, we talk about ecological models, which are tools that are able to predict not just one number, one variable, but a future probability using distributions in their core of ecological variables using mathematical and statistical methods. So when we want to model a tree with a computer, what do we do? So here, the slides is more like from a perspective of a dynamic modeler, so a person that acknowledge the importance of environmental variables in the growth of trees. So usually when we start modeling a tree with a computer, we start from thinking about what is the potential growth that a particular tree species can achieve in a particular site. And then we can apply some reductions to this tree growth due to environmental competition. For instance, if climate is not optimal, this tree is going to grow less. If there are competitors around this tree is going to grow less. And this usually how most of dynamic models works. They have a relationship between the optimal conditions and the climate and environmental variables. And then these are internally updated so they can dynamically simulate the development of individual trees. And then we don't want just to model a tree, but we want to model a forest. And forest is not just a composition of adult trees, but if we want to model the dynamics of a forest and not just the growth, we need to consider also two important ecological processes, which are establishment and mortality. And there are different ways on how to simulate and different scales, both spatial and temporal, at which we can accommodate establishment and simulate establishment and mortality. And so how this model work, and most of this, so the hardest part in these models is to derive all the necessary parameters for making this model works. So they are a composition of algorithm and equations which are driven by state variables, but also by parameters. And parameters can be of different types. There can be some generic parameters. They are usually embedded in the model code. That, for instance, is parameters that tune some algorithms of the different state variables. But then there are also some site or landscape specific parameters, those numbers that define, for instance, the slope of a particular portion of the landscape we want to simulate, the soil depth, all the environmental inputs. These are all, in a way, parameters, although we can make distinction what is an input, what is a parameter. And the more and parameters are also used to define and to differentiate between tree species that we want to simulate. There are this so-called species-specific parameter. For instance, a typical example is the shade tolerance of the tree species that are on a scale from 1 to 10, for instance. It's a parameter that can define how light demanding is a species or how temperature demanding is a species. So it's all this composition of numbers that can take a long time to when building a model, but also when you set up a model for running simulation. You will see some examples later. Yeah, and this is exactly what I meant also on upscaling processes from tree to the stand to the landscape. So when we simulate trees or stand, there are some processes. If we want to simulate forest dynamics, even at the stand scale, there are some processes that we must consider: mortality, growth, and regeneration. But then when we really increase the scale of application to the landscape level, so we consider spatially explicit interaction within the landscape, then that's the case when we can simulate also disturbances. But then if we simulate disturbances that act in a heterogeneous way in our landscape, we should also consider how trees adapt to disturbance, how this requires to simulate also seed dispersal, so to have also parameters that gives an overview on how this tree can germinate and at what distance. So there are a lot of processes that can be included in forest models depending on their spatial scale of application. And this is one of the most complex slides that I have in the presentation, because it shows the type of forest models for simulating forest dynamics. And there's not really a consensus on how to categorize forest models, because there are models that they are the natural derivation of these yield tables, which I introduced before. And these some examples inside this shape. There's some names of some existing models that derive from the yield table. So these are more empirical models that they are made for making some projections, but they can be they are not, if they do not embed climate, they are not how to say, they're not cannot be used for making long-term extrapolations in the future. While there is another branch of models that were more developed by ecologists. And here I put these two figures. This is the forester and here's the ecologist, because back in the 70s, there were sort of two figures that were starting modeling forest dynamics, but with two different perspectives. So the forester wanted to make predictions to understand their growth and yield. And the ecologist started to develop models to better understand how forest works. And so there is a large amount of models that derive more from ecological models rather than from the forest growth models. For instance, gap and succession models or process models, that those models that embeds a lot of processes and therefore require a lot of parameters. There are also models that do not simulate trees, but they simulate fluxes. They simulate, for instance, carbon fluxes or nitrogen fluxes. And these some examples of this. CBM is one of these models that simulates carbon pools, but do not simulate, for instance, individual trees, although there are some versions of it that it can. And then from these two type of, let's say, perspective, they started to develop models that can be used for making extrapolation, making simulations at a larger spatial scale. For instance, these are the so-called dynamic global vegetation models. These are models that can simulate the distribution of tree species and embeds also some ecological interactions, but not all of them. So they sacrifice some interactions to be able to simulate forest dynamics in a large scale. And then the world is not black and white. So there are also some models that were developed from ecologigical models and then hybridized and became more forest growth models. So these so-called hybrid models. And somewhere in the middle here, I put the landscape models that are the new generation of models that includes a lot of processes that are typical of process models, but they are able to simulate forest dynamics in a landscape. And usually these are sort of intermediate scale of application models, but they are among the most complex because they include both of these words. And in the next slides and in the examples in the second part of the seminar, I will talk more about three types of models. One is for CLIM, which is a typical gap model. and 2 landscape models that have been used in the past years. One is Landis2 and the other one is Island. Okay, this was my categorization of models, but usually when we talk about in the forest modeling community, we categorize forest models usually by in different ways. One is by scale of application, and by now I guess you understood what I mean by scale of application. We can simulate individual trees, or we can simulate stand or landscapes, and then of course the more fine-grained process a model includes, the more difficult it is to run simulations in the very long term. So usually biome shift models that are done to simulate very large areas, they sacrifice some processes in order to make it more computationally efficient. But usually the classic categorization is this one, is by purpose. Was it a model built for prediction, or was it a model built for understanding? So and in the community we talk more, is it a statistical model or an empirical model, or more a process-based model or a mechanistic model? And here's some example of these categories of models that are out there. Or another way is to categorize it is also by structure. Is it a model that is able to simulate the position of trees, or at least simulate some processes in a spatially explicit way? That's why we talk about spatially explicit model, or also called distance dependent model, or is it a distance independent model? So it's non-spatially explicit. For instance, for CLIM can simulate very well the interaction between climate and forest growth, but is not spatially explicit. While some other models, they sacrifice some other processes, but they are spatially explicit. And the last categorization is the one by Bugman and Seidel in the paper that they published a couple of years ago, where they sort of did the DNA of forest models. They took some dozens of forest models, the ones that are mostly used today, and this includes both landscape, stand, and dynamic global vegetation models, and they group them by complexity in their core module. So how complex are these models to simulate in their basic assumptions in terms of simulating growth, establishment, and mortality, and they sort of create the clusterized models by their complexity. And this is a slide I always like to leave here, that of course it's not that in the 70s they didn't have, they were not creative enough to simulate forest at a larger scale, like with landscape models, but they simply back then there was not enough computer power. So the development of forest models also followed the availability in computing power. For instance, now we can run simulations that back then was not even possible. So where can we find forest models? So in the past years, there has been some model comparison platforms that were developed that grouped the descriptions and linked to the different pages of forest models. The one is the CAPSIS. It's a web page that put together all the French-speaking forest models, or the EasyMIP is also a repository of that links all the different forest models. But nowadays, also the forest, like remote sensing, the forest modeling community is getting more and more democratized. So while before the developers were mostly using their own model and keep it by themselves, now it's good practice to have a nice documentation, and therefore most of models, they have their own website that are managed by their developers or also from a large community of users. That's the case of Landis2 and Island. These are 2 landscape scale models, and they're both very well documented. There are instructions on how to set up the first simulations. They are open access. Island, for instance, includes also a sort of internal Wikipedia for understanding how the model works. And the same as for other stand scale model like Sortie or 3PG, which is a widely used forest dynamic model at the stand scale. All right, so that's for just a introduction where forest models come from and how they were developed and where are we now. And then the next part would be more about examples and of applications from my experience and some from my colleagues. So if you have any question on this first part, before jumping into real world applications, yeah, take them. Also from people that are attending online, I suppose. Yep. Mm-hmm. Mostly stand and landscape. No, your classification. Mm-hmm. And the
I repeat the question. You told us about two classification, no?
Yeah.
Your classification.
Yeah, mine that I used to try to group all together. Yes.
And
then,
the classic one.
Yes, in a way. Yes.
In the classic one, you told us the complexity.
Yeah.
In the complexity, there is the ecologist point of view.
Yeah, in that, yes, if you want to say in a way, yes, it was, those models are all dynamic models. So they do not include growth simulators, which nowadays are still used, but not much in academia. So we now recognize the importance of climate change and how climate change and drives forest dynamics. So the models that are derived from empirical relationship are, yes, still in some way still used, but that classification is only about dynamic models. That's why they made a new term. They do not call them forest models, but they call them models of forest dynamics, MDF, in that paper, because they stressed that the importance of dynamic models that embed ecological interaction. So it's more from ecologists, but many of these models are now also used as a decision support. So they are the base for running simulations to provide also useful information for for forest managers. So now the two words are sort of getting all together in a way. So that's my classification that put these two figures here is to show from where different models come from. But yeah, the complexity is just about models of forest dynamics.
Okay, and another question, where these models are used most? You said in Italy.
Yeah, that's also in the second part. I can show you some applications, but they are mostly used by, let's say, at university there were some research groups that developed their own models, and they keep developing it. And that's, I will show you in the next slide the example of Forklim, for instance. In some case, there are models that are built in a specific biogeographic region, let's say in the Alps or in Central Europe, and they are mostly applied in the area where they were developed, because that's the area where they have been validated. But there are some models that have been built, for instance, to simulate forest in Central Europe, and then they were also applied in North America, but that requires a lot of new parameterization. I mean, you don't have to build a new model, but there are models that are generalizable, that can be applied in many areas. And the more a model, the more that is linked to how empirical is the model. So if it's a model that is more dynamic, it can be better generalized. So it can be applied in many areas, pending that you do a lot of parameterization. If it's a model that it's more from the forester, more empirical, it includes a lot of static relationship, then you need to re-parameterize all these relationship, not just estimate numbers in terms of parameters, and that they are hardly applicable in other areas. So this is the classic example of empirical models are mostly used in the area of application, and dynamic models are more can be applied in different areas. But I will show you some examples in the next the next part.
Okay, thank you.
You're welcome. So unless you have some other questions, I can move on. Okay, so what are they used for, the models? This is a typical. I like this graphics because it nicely summarizes the different steps that you do for using a models of forest dynamics. So in the core, you have the forest simulation models. You first need to estimate your site condition, the forest condition, and then usually provide the model particular inputs, and these inputs can be climate. So climate is not just historic climates to try to replicate and to simulate forest dynamics in the past, but also future climate. That's why the models of forest dynamics can simulate how forest is going to change also under changing condition. But then they was particularly for the models from the ecologists, they started to recognize the importance of these models for simulating management. So to try to compare management strategies and management scenarios. So that's why they became a useful tool to compare different silvicultural interventions in the long term. So to obtain not just the direct outputs, but then you can have link these outputs to indicators that gives you an overview of different scenarios in the future. And these scenarios, for instance, can be linked to decision support tools and to visualization tools, and can be converted into recommendation for forest managers. Because of course numbers says, but so if you have a visual interface, it's much more easy to communicate to the stakeholders and to people who really do silviculture in our forests. So this was just an overview on what are they used for. But I will, maybe you understand better when I talk about one particular model, just as an example, but many other models are similar. And this is for CLIM. For CLIM, it's a climate-sensitive forest succession model. And that's a model developed by ecologists, so by academics, by researchers, but then it's getting now more and more applied also by academics, but for forest practice. So at the beginning, it was a model that was built to better understand how forest dynamics works. The first application studies were done mostly to see if the model was able to replicate the potential natural vegetation of a particular area. And nowadays is getting more and more used for other applications. I'll show you later. But if you want to describe it quickly, it's a stand scale model that simulates a particular forest stand. So it is not a landscape model. It does not include maps, but simulates just one particular forest. And it is cohort based. Most of the models developed in the 80s, 90s are cohort based, because that means it does not simulate single trees, but it simulates group of trees with the same dimensions. And that's it's an assumption that was made mostly to speed up the simulation time. So if you do not simulate individual trees, the model runs much faster. And it is parameterized for 30 and more species in Europe, but it has also been applied in North America. As an input, it requires monthly temperature and precipitation data, so that's a must. It cannot be run to simulate without climate. But you also need to provide what are the water holding capacity of the soil, what is the nitrogen availability, it's just one parameter. What is the slope and the aspect of that stand that you want to simulate. These are all just numbers that you add to a specific input file. And then if you want to simulate starting from a real forest condition, you need to give them forest stand data. Share of tree species composition and what is the diameter and the height of trees. And then the model provides estimates of basal area, volume, biomass, number of trees, but also if you simulate harvesting, it also provides removed trees and volume. It is just to give you an overview, our model is made. We don't expect fancy graphic user interface. In some cases, developers made some interface. For Clim, for instance, is programmed in C#. And nowadays, more and more people are using R, the R programming language, to interface with the model. So you can create the inputs, run the model, and analyze the outputs all directly in R, while some other models, they have a user interface, but in R is nowadays is much more handy, particularly for stand scale model that basically simulate just numbers and do not include maps. How is it structured? So yeah, it is structured in this way. So you can see the different classes in C# in the code of the model. But if you just want to understand how the model works, it is there is one main submodel that is called plant. That's where the main algorithms of the model are included. For instance, the simulation of leaf area index, the simulation of diameter growth, the simulation of mortality, and the establishment. And then there are some submodels, for instance, the weather submodel or the water submodel, that they take the inputs that you provide them in terms of raw inputs of temperature, precipitation, and they calculate some bioclimatic index that then have an influence on the different processes like establishment or growth. And then there is the management submodel that was added. So that's it. For many years, Clim just worked with these three submodels, and it was not used to simulate silviculture or harvesting. But at a certain point, they started to realize, oh, this is a model that can be used to simulate silviculture and management intervention. So they added a management submodel that has an influence on establishment, when we can plant, or mortality. So harvesting trees, basically. And that's an overview of the management submodel that allows to simulate plantering, thinnings, or clear cuts in a different ways, target cut, group selection, and this can be defined by the user or can also be simulated dynamically depending on what the model simulates along the simulation. So you can say, okay, every 30 years simulate a thinning from above of 30% of basal area only on silver fir, and the model will do that. And then we'll take the pool of the harvested trees and put it into the harvested trees, and then you can get it as an output in the end. And that's what I meant by model evolution and development before. So there is not just, okay, developers just build the model and then that's it, and they use, but usually the developers are researchers that keep making the model, their model, evolve. So at the beginning for Clim was done for comparing environmental gradients and to understand potential natural vegetation. And nowadays we are at version 4.1, and then it included many other functions and multiple variants, and it has also been improved in the last years to better capture forest dynamics and been validated with in other areas. Okay, and in my case, during my PhD, I was involved into, so I did my PhD at ETH Zurich, where I was involved, my main task was to use the Clim model, this model in some case study area in this large collaborative European project that was called Arranged. We wanted to evaluate strategies for forest management under climate change. And so this was a big collaborative project with 16 partners in 7 case study areas. And in each of these case study area, there was a modeling team. And the modeling team was responsible to gain data from the managers and to parameterize one or more models to be applied in these regions, with the main aim to assess the future provision of ecosystem services. So in a nutshell, what we did in this project was to collect a lot of data from these case study areas, climate change scenarios, forest stand structures and management prescriptions that were fed into these forest models. So each of these forest models were initialized, and then we ran simulations of forest dynamics in the future under different scenarios. So under different management and under different climate scenarios. And we linked the outputs of these models to ecosystem service indicators, so we can give an overview on how ecosystem services such as timber, carbon sequestration, or protection are going to change in the future in forests that had a particular common feature were all in the mountain areas. And to make it even more realistic, to bring something. And what I did was to work in the Dinaric Mountains, which is this is a landscape in the Slovenian Alps, no, in the Slovenian Dinaric Mountains, which is just out south of the Alps, to study the impact of climate change and different management alternatives in this landscape. So this was a mountainous area. We had more than 1,000 forest stands in this landscape, and which we simplified with stratification. So we defined 23 representative stands, and each of them we initialized them with the for-clim model, and then we ran the simulations in the future to understand at different elevations, a different tree species composition, how these forests are going to change under different climate scenario. In this case, under current forest management. So we try to replicate as much as we could what is going to happen to this forest if management, if foresters we keep managing as they manage them at the moment. You can see here the different changing basal area of tree species, and the dot and the dashed lines represent the different climate scenarios. And overall, with our model simulated a strong decline in the share of silver fir, not only due to climate change, but mostly due to browsing, because the model also allows to simulate browsing intensities by deers. And silver fir, Abies alba, is a very is well known to be favorite by deers for browsing in regeneration. And so we could show that this forest, if they continue to harvest in this way, so to harvest the same amount of Abies alba, they will likely be dominated by beech in the future. So there were case study responsible for this project in Slovenia. They did a workshop with the forest managers, and the forest managers, they provided them some information on how to define and design management interventions to generally protect and promote conifers, and we re-implemented them in the model, and we ran simulations showing these alternative management regimes that in the end shows that silver fir is going to decline, yes, but not in the same magnitude as by keep managing as the current moment. So we could show the potential of changing management interventions to following the goals of managers, and these were converted into recommendations for multifunctional forest management strategies under climate change. That was the main goal of this project. But the goal also for my PhD was try to have an overview of the future ecosystem services from multiple forests under climate change and management. So for this reason, I do not, this relates also to one of your questions, where these models are applied. This model was built for the Swiss Alps, but then we applied it in all these 4 case study areas, so from Spain to France, Austria, and Slovenia. So we applied the for-clim model in different forest stands under different management scenarios and under different climate change scenarios, all in combination. to evaluate future ecosystem service, to provide an overview on how ecosystem services are likely to change in Europe. So this is less local case application like the one in Slovenia, but it aimed to provide an overview of ecosystem service from given the important differences that we have in these mountain areas. So these are all the model outputs that we got from, so we ran, again, for CLIM, it's a stand scale model. So we ran many stand scale simulations, and we linked all these outputs that were like a simulated volume of different tree species. We linked them with these ecosystem service indicators that let us give an estimate of the amount of timber, carbon, biodiversity, and protection function that these forests have. And so it's that's why when you run the simulations, the work is not done. You can also post-process a lot of your model outputs, so to convert them in a way that give an indications of other services and not just the tree species composition, for instance. And well, this is a bit complex, but it shows how the different indicators of timber, carbon, biodiversity, and protection against rockfall and avalanches are likely to change under the current climate, moderate climate change, and strong climate change. These are the different scenarios that we evaluated. These are only 3 out of 5 climate change scenarios in the 5 case study area. These are just one example of a stand, so we try to put everything together. And the different colors are the different management scenarios. And basically the area of these radars gives an indication of what is the total amount of ecosystem service provision in these forest stands, and how this is likely to change if forest is going to change in the future. So, and we try to summarize it also with an index of multifunctionality, which is this area of these radars, to try to understand what is the best forest management that we can do to maximize these ecosystem services. And this, of course, it depends. It depends on the case of the area that we consider, the region, but also depends on how we simulated management. All of these areas, they had a different management system. In terms of also business as usual and alternative management, they were all different. So in some cases, business as usual was doing good enough. In some cases, we needed to make some changes into management decisions. So it very much depends. The more you go into local scale applications, the more the situation is different according to the magnitude of climate change, but also on the local conditions that you have in your forests. And that's a picture that we also got from this latest study. So the one on ecosystem service was a study that I did in 2016, 2017. But now since I'm back in Italy, we try to use the same model to focus only on the protective effect against natural hazards. So we wanted to understand if climate is going to change and forest is going to change, how this is going to affect the protective function of forests in South Tyrol. And by protective function, I mean the capacity of the forest to buffer natural disturbances such as rockfall and avalanches. And this is South Tyrol. I will show you a bit later, describe a bit later the province where I'm working. And most of the area is, the surface of the province is forest. 50% of the surface of South Tyrol is forest. And among these, 58% of this forest is categorized as a forest that protects something. And 24% is a forest that has a direct protective function. That means that it's in between a release area of rockfall or avalanche and protects an infrastructure, a road or a town. And I guess it's very similar here in the mountain areas of Lombardia. So what we did was to select some representative forest stands to have an overview. Of course, we could have selected more, but in this case, we selected subalpine and mountain spruce, fir and beech forest, and larch and Pinus cembra and Swiss stone pine forests. And we selected these 11 protection forest sites and ran simulations with ForClim on the different climate change and one forest management scenario. And we focused only on protection indexes, index that protects against the avalanche, and that gives an indication from 0 to 10, what is the capacity of our forest to protect against rockfall and against avalanches. And this is just an example. I know it sounds abstract, but these are real forests, and differently from the project I did before, where I collected extensive data from across Europe. Here, these are forests where we collected data ourselves. So this is one side, it's a beech forest, and this is how the ForClim model simulates the development of this beech in this case, is without climate change. It still shows that the forest in the future is likely to be more dominated by oaks in this particular site. So in these sites, we also collected diameter and height of the trees, and we use them to initialize ForClim. This is another site in a mixed forest in a mountain belt. It's mixed between Norway spruce, silver fir, and beech. And if you go to this forest, you see that in the understory, sorry, there is only beech. So it's really interesting to try to picture it, the forest of the future in this site, knowing also that spruce will have problem with bark beetle and coping with future drought. And again, this lot of simulations under baseline climate, but we focus on different climate change scenarios. And then we could see, and these are the different, 6 out of these 11 representative protection forest stands that we selected. And we could show that the impact of climate change depends also on the severity of climate change, because in some case, if you look at this beech-dominated site, under the most moderate climate change projections, there are not big changes between current climate and climate change. But then if under severe climate change, then the model simulates strong mortality of beech in this site. So we cannot really also talk about forest under climate change, but we have to acknowledge that there is a range of future scenarios, because we don't know we don't really know for certainty how climate is going to change, if it's going to change moderately or very strongly in the future. And this is how, yes, same radar plots, but in this case, they only show the difference in the avalanche protection index and the different rockfall protection index, this RPI. And one means that it's a protection against big, in this case, I think it's small rocks, and RPI 2.5 and 5 indicates the protection against medium and big boulders that can roll down the forest. So because the level of protection that the forest can give you is also depends on their structure, but also on what it protects from. So whether it's more effective to stop small rocks or big rocks. So for big rocks, you need bigger trees. For small rock, you need smaller trees, but then you need a higher density. And this index, they show you, they can give you an overview of the level of protection depending on what does it protect. Okay, and before I mentioned about forest disturbances, and which I think is an important aspect to consider nowadays, because so far I have shown only the direct impact of climate change, how forest is likely going to change according to these models if temperature and precipitations are changing in the future. But we know that there is more than just changing temperature and changing precipitation, but what is more concern in the future is the increasing disturbance rate that the forests are experiencing nowadays. So the forests are getting more and more disturbed by wind, fire, and insect. And what is also more worrying is how these disturbances are going to interact non-linearly in the future. So we know that following a strong period of drought, we might have more outbreaks of insects, or even after wind, we will have insect. The case of after the windstorm Vaya, after a couple of years, then we had the strong bark beetles outbreaks, and that's same for other type of pathogens across the world and in the different forests. So this is just what we experience here in Italy. I'm not sure if you have been out in the field here and you've seen the effect of bark beetle, which is not only due to increasing increasing climate change, but also because of it interacts with other disturbances. And so if we look more towards the future, so now I think we are in an era of not just acknowledging ecosystem services, but to maintain with forest management, we should target the maintenance of ecosystem service, but also to focus, to put a strong focus on making our forest more resilient to global change, acknowledging that they are a complex adaptive system. And so we should intervene in our forests. We should use silviculture to maximize also the way that the forest can self-reorganize after a disturbance. So to make it, and this can be achieved by making a forest more diverse, more structurally and functionally diverse, but also looking at multiple spatial scales. So not just stand, not just landscape, but from tree to stand to landscape. And nowadays we have models that are able to accommodate all this hierarchical scale of application. But also we should also, with our models now, try to make projections to simulate disturbances. We can acknowledge and see what is going to happen to our forest if they are suddenly disturbed, and how they are going to recover. But disturbance, they have a different effect in space. So it's hard to use a model like for CLIM to simulate a disturbance, knowing that it only simulates one stand, because a disturbance might affect one stand, but also what is around. So the best way to simulate and try to mimic the effect of a disturbance, such as a wind throw, a bark beetle outbreak, is to use forest landscape models, which are models that are by default, by nature, spatially explicit. So they consider seed dispersal, they consider the movement of trees across the space, and they can at the same time integrate multiple forest types, conifers, deciduous, mixed different stand types within a spatially explicit feature. But then they can still integrate ecological processes. For instance, we can, in a cell, still simulate the interaction between forest growth and climate. But on the other hand, they are more computationally intensive. They require more computer power. They are more time consuming to set up and parameterize, because they require not only forest data or climate data or the typical inputs, but they also require maps, and they also require to set up the landscape in a way that you capture the difference across the space. And one of the first models that was developed for this is Landis. And what I'm showing you here is Landis 2, is like the second version of Landis. Landis is the father of all the forest landscape models. And Landis 2 is like the natural evolution of Landis. It's a landscape disturbance and succession model. And it's not, I call it a model, but it's not just a model. It's a framework for simulating forest landscapes, which includes natural disturbance, harvesting, and is based on simulating biomass. So it does not simulate individual trees, but within each of the cells, it simulates the biomass of the tree species. And it's very flexible in terms of choosing the time steps and the spatial resolution. And what I mean by that is not really a model, but it's more a framework, is that because Landis is built by extensions. So you install one core version that is basically a compilation of functions that allows different extensions to call and to interact between each other. So you can simulate forest dynamics as or succession with different extensions, and therefore allows the user to define what level of complexity you want to simulate forest dynamics. And then you can activate or not optionally or disturbance module, management module, or output modules. So it's really, really flexible and is well documented. It is spatially explicit, but in a way that it simulates dispersal and disturbance and harvesting across the landscape. But within each of these cells, there are non-spatial explicit processes that are considered. So they, within each cell, it's like a morphoclim within each cell, but then it's able to also simulate how trees disperse and can move across these cells. And within the cell, you also have species-specific attributes that you need to parameterize. So as you can understand, including all these things gets more and more complex. But and this is just an example on how disturbance are integrated in a complex dynamic model like Landis. This is one of the extensions that allows to simulate insect disturbance, which is it simulates insect outbreaks following different temporal patterns. And so you think about it, you have a forest within this landscape, but then only some species are susceptible to a particular insect. So if you say, okay, I just want to simulate outbreaks of bark beetle, then the beetle will only affect the spruce, and therefore it calculates a site resource dominance, so how vulnerable is one particular cell to a particular insect, and then depending on different functions, it simulates stochastic outbreaks of these insects and how big they are depending on climate condition, but also depends on what the insect finds in terms of tree types within the model. And I used this forest model during my project in Canada, and the main aim was to couple forest landscape models with the principle of network analysis. So to principle of functional diversity. So not only to see the forest by a composition of tree species, but to see it as a composition of functional traits, and to use the network analysis to try to recreate, to see forest landscapes as functional complex network to plan management interventions differently across the landscape. But you can see better here. So for instance, we take the principle of functional diversity, functional redundancy, structural diversity. These are basically calculating the different functional traits that we find in one cell of in one particular stand, for instance, and then use the principle of connectivity and the modularity of the networks to depict this landscape that you see. This is an aerial picture from Google. This is a fragmented forest landscape, and following this principle, if you just want to simplify, we can create the landscape as a network. Each of our stand is a node of this network, and this is linked by different level of dispersion of functional diversity. So how much a forest stand is able to disperse traits of the tree species that is for which is composed from one stand to another. And this is sort of a way to to try to plan interventions in the landscape so we can intervene where is really needed. So we can intervene in areas that are required to be diversified with mixed plantation, with promoting functional diversity, or to make assisted migration of or enrichment planting, so we can create a more functionally diverse landscape, because we know that the more a forest landscape is functionally diverse, the more is resilient to particular disturbance. The more we have a forest that is diversified, the more we have a lot of traits, and the faster will the forest will likely to recover if there is a disturbance. So that was a lot of that. This was just the concept, but we wanted to test it within with a forest model, and so we took a representative landscape in southern Canada, and then we parameterized it within the forest landscape model Landis, and we used it to simulate changes in forest types at year 2100 and the climate change and management. So you can see here under different climate scenarios, these are the outputs of the prevision, like forecasted changes in forest types under different scenarios. So for instance, the orange ones are the high climate change scenario that you can clearly see that the model simulates an increase in deciduous species and a decrease in boreal conifers, and this was sort of expected. But what we could also do with these models to project how the productivity of this forest is probably going to change, and as we can also simulate net primary productivity and how the photosynthetic capacity of this forest is going to change along the year, and comparing this, for instance, the current time, 2015 in that case, with the end of the century. But my main goal was to try to compare different management strategies. So we simulated management like business as usual, which is silviculture as it is currently done now, following the classic management units that are in this landscape that divides the forest into private forest, public or public managed, or natural reserves. And we also simulated conservative climate change adaptations, because now forests in this area are already planting some future species and doing some enrichment planting with species that are known to be more adapted to future climate. And then we simulated a scenario that is more hypothetical. So we really discarded the current management unit, and we use the principle of this functional network to create priority areas. So we saw, okay, this area, there are some areas that are not diversified enough. So here we intervene with silviculture before, and then we leave some other areas that are already diversified enough for later. So to also optimize the level of intervention to some areas that need really priority in terms of making the landscape more resilient. And then we also simulated biotic disturbances, so simulated impact of insects that are currently in the landscape or that are likely to arrive in the landscapes. We have a model, so we can play with it, and even making some scenarios that are sort of absurd. For instance, these 3 insects are not present in the landscape, but if they arrive in 30, 40, 50 years, what will be their potential impact in this landscape? So we could show how susceptible is this landscape to these insects. This is a very destructive insect that kills ash trees, Fraxinus, and is the emerald ash borer, and which is killing most of the trees in Montreal, in Toronto, in many cities all across North America, but has not been detected in this landscape. So we could show that, okay, this landscape is not much dominated by Fraxinus, so it would only affect some minor areas. So the overall susceptibility of this landscape to the emerald ash borer is 5.6, but on a scale from 1 to 100. But then if this insect, the Asian longhorn beetle, it's an insect that can affect many broadleaf species, then it's a very high destructive potential. So we could also create maps and show where are the most susceptible area of the landscape to particular insects. Okay, this I can skip it, but I just wanted to focus on these indicators of ecological resilience. So we try to summarize it. What is the level of future functional connectivity in the y-axis, functional diversity in the x-axis, and structural diversity in the which is the size of the shapes. And these are all my different scenarios. So you can see a lot of combinations here. But generally, what we wanted to show is that by functionally diversify the forest with management using our functional network approach, then we can achieve a higher level of ecological resilience. The forest is likely to be more ready to cope with the potential disturbances like these insects. And what I am proud of this work is that it stimulated a very large project that is currently undergoing. It's just started now. It's called Diverse. It's a project that it aims to test these principles not only in one area, that was this one, but in multiple landscape across Canada from east to the west coast. So first, we want to test the functional network approach and simulate forest management strategies, but then really to make it together with the managers of these forests, so they can give us important information on how they can realistically change silviculture so to make forests more resilient to global change, and also to increase the acceptance of the use of these models to forest companies, First Nations, because there are also different communities living in this forest in Canada. Okay, and these were some examples of research applications from my past works. And if you have any question, we can take maybe a 2 or 3 minutes break if you have some question, and then I have a final part with some latest work that we're doing in South Tyrol.
Which parameter of parasites were considered to establish to draw the maps of vulnerability that you showed previously?
Yeah, there are, so each insect, I would say, we call it a disturbance agent. Each insect disturbance agent that can affect the landscape is parameterized with a table that defines what are, for instance, the preferred host trees that this insect can affect. For instance, there is an insect that goes preferably on maple, on acer, and so you say, okay, this insect prefers red maple is the favorite tree, but then you have a second and minor host, so you can define a list of species that are the susceptible species to this insect. Then there are some parameters that defines the frequency of outbreaks. Let's say by literature, by knowledge, we know that some insects they affect the forest in temporal outbreaks. Some insect as every 7 to 10 years, some moth that the spruce budworm, for instance, is an insect that affect boreal conifers, but usually it has a return time of 40 years. So in that case, you simulate outbreaks, but intense outbreaks only for every 40 years. And then there are some dispersal parameters that defines how much this insect can move across the landscape. Because there are insects there are beetles that can, for instance, move 1 kilometers, and then there are insects that are more Lepidoptera. In that case, they can move to a large portion of the landscape. So there are different. Usually, there is one input file that defines all these parameters, and then you run the model, and then there are some distributions that drives the simulations. So you define some parameters, and then distributions within the model effectively simulates the mortality of the simulated trees depending on these parameters. So for instance, if you saw this, the Asian longhorn beetle, you saw these big circles here, is because we defined that this, if detected, so we assumed, for instance, that this insect can be detected in the landscape in 5 places, but then if detected in 5 places, it can only move to a radius of 20 kilometers, not more, because it doesn't move much in the landscape. But the budworm, for instance, it flies a very long distance, so it can affect the whole landscape simultaneously. Yeah, and usually are parameters that comes from literature, from other papers. So yeah.
The ecosystem services valuation was made on expert base that you show us, the Pentagon.
The indicators, how they were derived, you mean? Or so they were simply or the type of ecosystem?
Il grafico ragnatela.
Sorry?
Il grafico ragnatela.
Sì. So they were, let me show you. This one?
Yes.
So this, we had to make some simplifications. So you see, these are the model outputs. So we wanted to target 5 ecosystem services, and these was decisions that were taken in the context of this large European project. So we wanted to standardize the type of ecosystem services that for making assessment in the future. And so we focused on timber, carbon, biodiversity, and protection. And based on, I think that was a specific task within the project to ask stakeholders what are the most important ecosystem service that you need from your forest. And then we try to, among them, to define what are the common one in these 5 forest types, in these 5 areas, and the common one were these 4. So there were some areas that recreation was more important. Recreation was also important, but it was not in another area. So these were the 4 common ones. But some other colleagues, this was a very large project. This is just one study we did in this project. They also ran some evaluations for cultural ecosystem services, and this study does not really. One of the limitations from this study, in my opinion, is that does not consider that ecosystem service importance is going to change in the future, because for maybe in some decades wanted is not very important in this area, or protection will not be that important. So we just considered, we wanted to summarize and focusing on these 4 services. And among them, we also had to decide, okay, what indicator do we consider that gives an overview of this particular service? For biodiversity, in this case, we chose deadwood volume because we know that the more deadwood you have in a forest, usually it was more linked with the diversity of beetles, and then it's more linked to the diversity of birds. But then we could have chosen another indicator. So when you work with ecosystem services, there are many decisions they have taken a priori.
Okay, okay. Understood.
And these results were presented also to stakeholders, but that was not part of my work. I was more doing the modeling part and the future assessment.
Okay, thank you.
You're welcome. Oh. Do you have any other question? What time is it? How much time do we have more? Until 3? Oh, no, until 4 we said maximum. Okay, so we have 15-20 minutes for this last part. And I just wanted to show you, I don't know how many of you are familiar with South Tyrol. Have you ever been to South Tyrol, to Alto Adige, which is, I just give you always a slide to show. So we are here today. We came from the Passo del Tonale, and Bolzano is here, and there's the administrative capital city of South Tyrol, which is an autonomous province. So it's there's a larger degree of autonomy comparison to other regions in Italy. I'm not sure. Are you all from Italy, or is there anybody from not? You're not from Italy. You know South Tyrol? Oh, okay, perfect. So it's a very mountainous province. It's 50%, but 50% of the land use in South Tyrol is forest, mostly conifers, but we also have deciduous forest in the valley bottom, and we have different forest types, going from the more sort of sub-Mediterranean forest in the lowland to mountain beech forest, mostly spruce forest, but a lot also of larch and Swiss stone pine. So we have a large diversity of forest, and what I've been initiating in URAC, in our research institute, is to study the evolution of some of these forests by representative study areas. And given our experience, we try to use different models at the stand scale and also at the landscape scale. So at the landscape scale, we are focusing on a study on treeline expansion, but also using models to understand how forest types are going to change along elevation, and with the impact also of disturbances, which the typical disturbances are wind and beetles. And we selected some forest types, some forest landscapes, one in Val Venosta, in Pinchgau Valley, and the number 1. The 2 is just outside of South Tyrol. It's in the Stubai Valley, but we already had a landscape parameterized for this area, so that's something we've been doing. And the 3rd one is in progress in the south, near Dolomites. And then we also, thanks to a long-term project on biodiversity, we were able to collect a lot of data from different forest types, forest stands that are distributed across the province, to study stand dynamics and climate change, but also protection against natural hazard, which is what I showed before. Okay, and the last model that I will talk about today is Island. And Island is a sort of one of the newest forest landscape models that have been developed. And the main new feature of Island is that it's able to simulate individual trees. It simulates the position of individual trees, and it can also simulate them across a large landscape, and can also include disturbances. And it is also very much process-based, so it can simulate climate change impacts, the effect of climate change, but also the effect of other environmental variables on forest dynamics. It is spatially explicit, and it can also simulate above and below ground carbon stocks, carbon pools, and is built for complex terrains like in the Alps. So it is very powerful because it can simulate from individual tree to the landscape, but it is very complex. It requires many inputs, and it requires a lot of time to calibrate it to be used in an area because of this complexity of the ecological processes that can simulate, and or in some cases it must simulate because it's embedded in the code. And what we have been doing in the past couple of years is really to collect the data to try to create a virtual replicate of the forest within the island model in the Vinschgau Valley in the Val Venosta. And here is the Passo dello Stelvio, it's right here, and this is the municipality of Prato allo Stelvio, and this is with the area where we're going towards Switzerland and Austria. And so it's a sort of a super landscape because we have three valleys, the Valley of Strafoi, the Valley of Solda, and the Valmazia, where we have our long-term ecological research network from URAC, and a large portion of the Parco Nazionale dello Stelvio, which is an area that we're starting now working on also with the idea then to study the impact of changing forest on biodiversity. But setting up a landscape was not, it's hard in a model like this that is very complex because you need to estimate a lot of data, and not only for one stand, but for how the heterogeneity of this landscape. So you need information on soil depth, soil texture, available soil nitrogen for the whole area. If you want to simulate carbon dynamics, you need to have estimates to validate carbon simulations on coarse woody debris, litter carbon, and soil organic matter that usually are hardly available. You can derive them from inventory points, then make an imputation in your forest communities. And so it is, when you work at the landscape level, it's really not feasible to go out in the field and collect the data to implement in your model like we did with the ForClim. Then you need climate, so you need historical climate, you need climate change projections, but then you cannot really just feed it to the model as it is. You need to pre-process it in a way that you can recreate, in this case, homogeneous climate regions to minimize the inputs to your model. Otherwise it will run very slowly, and when you need to run a lot of scenarios, then you want the model to run as fast as possible. And then you also want to simulate starting from the more actual forest conditions. So you need information on forest cover. They usually are derived from remote sensing data, or forest types, species shares, the stand volume, basal area that you can get from forest management plans. Or if you're lucky to have a LiDAR campaign that for which you have data at the individual tree position, there is also the possibility to initialize these models with LiDAR data, but these are hardly available for such large landscapes. And then you need, if you want to simulate forest management, you also need information on how forest management is currently executed in such a large area at stand or at the management unit level. And then when you have all this information, you cannot simply put them into a table and say, okay, this is my initial condition, click, the model starts. But it's always more complicated than it is. So you need to make sure that the dynamics, so that the relationship that you have in your data are in balance or in line with the relationship that you have within the model. So usually to set up the model, as we say, initialize a model, you need to run some special iteration simulation that allow you to recreate the initial conditions, so the starting condition from where you can start the simulations. So usually this is done by defining some target values that you have. You say, I want this tent to have 90% Scots pine and then 10% spruce with this age, with this diameter distribution, and then you run a spatial simulation backwards, and then the model will just go and back to recreate the initial conditions. So they are, it virtually recreate the trees within the landscape. Then you can visualize it in this way. For instance, you can see the the whole landscape, and the different circles here are the different species that compose my landscape. And then you can also evaluate on how good is the model to recreate potential natural vegetation. So you you run the model backwards for, let's say, 1,000 years, and you let it grow, and you see how good is to recreate the different dominant species along elevation. This is these are the three valleys, and the more you go up here, you have subalpine mountain to subalpine forest. So here it's mostly Scots pine, spruce, and larch and stone pine. And the model here we evaluated that is doing pretty good job in replicating forest types against the vegetational map that we have from the foresters. And what we are currently doing is to run the first simulation experiment. So to want to see how these forests are likely to change in the future under climate change and disturbance. For this, you need also climate change projections. And the nice thing about this model is that the warmer and the drier it gets, the more it is directly linked with disturbances such as bark beetle. So if you activated the bark beetle module, it embeds some relationship between climate and bark beetle, so that we are able to simulate outbreaks as an emergent probe feature of climate. So you can see here, these are the cumulative number of bark beetle damages in the next decades. So the projections of how much Bostic typography bark beetle is going to affect our landscape. Mostly, you see where here it's dominated by spruce, the green area. And you can see that under climate change projection, the strongest one, the model simulates almost a double number of damages comparison to the running the model under historical climate, because we know that if climate is going to be drier, then the beetle is probably be able to do more generations. They would be coming out of the winter earlier, and then it will be able to reproduce twice as fast. And this shows the number of bark beetle generations that can likely increase under climate change. These are just preliminary simulations. We haven't really quantified it yet. And of course, the more beetle we will have in the landscape, the worse will be for Norway spruce, because this shows the disturbances, the volume disturbed. Of course, these are just projection. We don't know that in particular year there will be a bark beetle outbreak, but the trend is this one, that we know that we need to think about beyond the Norway spruce, and knowing that we must diversify this forest, but this requires also an adaptation mentality by the foresters to accept other type of wood out of the forest. And this is another study we're doing, and this is in Austria, in the Stubai Valley, just outside of the Brenner Pass, going towards Innsbruck. On the left, there is a very long valley that where they already ran the island model, and this is the work of the PhD project by Sebastian, who sits right there. So if you have some questions, up to him. And what we wanted to do very quickly, since we had the landscape already parameterized, we simply wanted to see how treeline is going to, our forest is going to expand in the future, hypothesizing that grassland, the current pasture and grassland at high elevation are going, if are going to be abandoned, how fast is the forest is going to expand at high elevation. So it's a study on treeline dynamics. And we thought about this could be done relatively quickly because the landscape was already parameterized, but then Sebastian also had to re-initialize the landscape, so to allow the forest to expand to this other land use, which are grassland and meadows at high elevation, and then also define what is the alpine treeline ecotone or the forest grassland ecotone, which is this belt where between the line of forest, the so-called timberline, and the last tree that is able to survive at that elevation. So, and then we ran the model under climate change scenarios, also including potential natural disturbances, wind and bark beetle, and forest management, hypothesizing an abandonment of these alpine areas under climate change. And you can see this is the initial condition with mostly spruce, and this is mountain pine, Pino Mugo in the upper elevation, and then these are the results of the simulation at 2100, at 2200, letting the model to expand so that trees can rapidly colonize the available areas. And no surprise, we found that the forest is going to shift very fast, not just because of climate change, but because of the current tree line is much lower due to past land use, as you can see here. So we have areas where we have open spaces, and these are currently maintained as a grassland through pasture, but we also have trees that are able to grow much above this line. So as a no surprise, we found that climate change will not influence much the speed of the species shift, but it will have a strong effect on species composition and the stock in the tree line. This is the forested area, and these are the elevational shift of the different tree species. And you can see that the dash and the solid lines are basically in the same line, that there are no big difference between no climate change and climate change, but that the shifts are more pronounced in south facing slopes than in the north facing slopes. And but the main differences due to the climate scenarios were observed between no climate change and moderate and high climate change, not in terms of how much the forest is going to, how fast the forest is going to change, but how the forest is going to change. So in terms of basal area of tree species, climate change will likely promote an increase in stock and forest and differences in species share at the tree line ecotone, in this particular ecotone. Okay, and we are almost at the end. This is the last simulation experiment, and this is a bit different than the others. It's not with dynamic models, but more with it's done with species distribution models, but it's one of the only way to work at a large scale. So with this, we try to explore what is the future climate suitability of tree species under climate change. And so this can be done, these are sort of statistical models that using presence, absence data of the main tree species, in this case taken from the National Forest Inventory or from the biodiversity monitoring, our biodiversity monitoring plots. We can feed some statistical models with environmental predictors, with climate data, soil data, and climate change projections to obtain suitability maps, what is the current and future species distribution, which is not the species distribution, but is more the climate suitability of tree species under climate change. And I think this is quite important because it shows although it does not really include the dynamics, it does not simulate how forests establish growth, mortality, etc. But it can give an overview of forest managers that are thinking about now to promote some species or to plant some species, in this case, Abies alba, silver fir, if they want to promote in the future, or in this case for Norway spruce. We know that by 2100, the red areas will not be climatically suitable anymore for this species. The blue areas are those that both now, in the present, and in the future, the climate will be suitable for this species, and the green areas are those that are likely to be suitable only in the future, by 2100, so at higher elevations. And these are projections that shows how climate is going to change very fast, and that some species will not, that currently present, for instance, in these red areas, in 100 years will not be able to grow as well as today. But that doesn't mean that this species will collapse or die immediately at 2100, but that means that if now we are thinking about adaptive forest, adaptive management, and what are the species that are suitable in the future, these maps can give an indications to plant or not to plant some species in some areas. So, and with this, I came to an end of today's seminar, and I hope that I provide you some interesting information on how simulation models are useful tools to evaluate future forest development and management under climate change, to at least let you understand that there are not just one type of forest models, but there are many. It's a big world out there, but also that these tools can also be used to better understand ecological interaction, not just to make predictions. The challenges, I think, for the next years would be to make managers and to integrate these projections for long-term forest planning. So to really use these models that can aid management decisions also at the administrative level, and that foresters are starting to recognize the usefulness of these tools. And this, of course, require better science practice interfaces, because usually it's researchers that use these tools, like me, like us, also Giorgio, and but then it's hard to just provide as forest managers to use these tools. So we need to really work together between research and practice to better understand how to build more resilient forest. And that's it. Thank you for your attention. If you have any other question, I think we are in time. I don't know if anybody connected online is being able to follow everything. Yeah, the long day, yeah? Yes. Martelloscopio. Yeah, this is also, yeah. This is also a sort of a model of which we
discussed about the future of that small piece of wood.
stem. Yeah.
Yeah, and in that case, it was about the Fagus sylvatica, the beech. about bringing the dominant, being the dominant species?
In the future or now?
No, in the future, because now the dominant species is
Spruce.
spruce. Yes, there was just one silver fir, which studies said could be a good candidate for the future. And so in our silvicultura, in our
Culture, yeah.
silviculture, we try to improve the beach potentiality.
Interesting. Yes. Micro.
Does the model take into account the possible speciation and to adapt to
Genetic adaptation,
Yeah.
like subspecies or population?
Yes.
Yeah, that's a big debate in the forestry community. Some models they do. It all depends on the parameters. You can, if you want, if you have knowledge of an ecological characteristic that differentiate a species from a subspecies or from a speciation, as you say. But in the end, what we're talking is an individual of a species that shown different ecological characteristics. It can be included in the model. Yes. By default, not. It's not done, and by default, these models do not consider that ecological characteristics might change in the future. So they just give an example, does not consider that one species might change its shade tolerance in the future. For this, you will need to make these parameters dynamic so that they change based on something. So by default, yeah, usually variations in genetics, they are not considered. But if you have the knowledge, they're easily implemented with some differences in the parameters. And that's something I've been heard about since 10 years, but I think there are some models that includes genetic adaptations or over varieties or species. Yeah.
But maybe they are not comparable with the change of climate, the change in genes.
When you talk about future scenarios, how can you validate? It's really hard to validate in the future. You have to trust that the model is able to replicate as best as you can the ecological processes that you have with your validation. If you have, like, let's say, a time series that you can validate your model, then you can trust that the process that you validated are also good for the future. But there is no way to know that is. That's why we don't really make forecast like weather forecasts. We do more projections, and then these models are used to be run with a wide range of scenarios that gives you an indication of what if in case of different scenarios. So you always have a range of outputs and not just one output. Va bene, grazie per l'interesse, per aver seguito anche da casa, spero sia stato interessante. E qua ci sono i miei contatti, eventualmente se qualcuno vuole contattarmi, siamo qui. Ok. Grazie a voi.